Hello, this is Chris with a short video on basic routing and subnet concepts. The subtitle here is Getting from Exmouth to London Without Directions. And in case you hadn't noticed, I'm not from around Wisconsin. I am from England and I lived in London while I was there, and I had a brother who lived in Exmouth. I hope that you recognize my homeland from this map. On the right here we have the map of England, Scotland, Wales and Ireland. When I was living in London, I would go and visit my brother down in Exmouth. That's where this arrow is pointing out right now. And on the way back, I didn't need directions to get back home. That wasn't because I knew the country so well. I had not really travelled down to Exmouth much in my time, and when he moved there, I didn't know the roads, and when I took my German wife out to see him, she was asking me for the directions to get back to London. And I said, well, we don't really need any. All we have to do is follow the signs to London. This was very disturbing to her, but she found out that on the way back it was in fact the case. What happened was that we drove out of Exmouth along the direction that the main town was pointing. Had a traffic circle, and there's one exit pointing towards London. We took that exit. The next major centre we got to was Yeovil, and Yeovil had signs for Cardiff to the north, Cornwall to the west and London to the east, and again we took the exit for London. We got a bit further and got to Salisbury. There was an exit pointing north to Birmingham and an exit pointing to London. We took London. Same thing at Basingstoke. There were other options for exits, Southampton, Reading, but we took the one to London, and then we finally ended up at London. Now this is very similar to the way that IP routing works within a network. When you have an IP packet, and we'll talk about what that is in a little bit, when you have some traffic that is trying to get from its source, in this case, in our analogy, Exmouth, to its destination, in our analogy, that's London, it doesn't have to have, or no one element in the network has to have, a plan of the complete path from source to destination. All it needs to know is the next place to get to on the path. And that's just the way that I navigated my way from Exmouth to London. I just took all of the signs for London when I wanted to get there and ignored the others. So let's extend this to get a little bit closer to the way computer networks actually work. So how do networks actually direct packets, these little chunks of information that they want to send around? And very much like USPS, the United States Postal Service. Here you see a letter. It is from me, and I'm using the MATC address Truax, and it's going to Damien Roth in the downtown location. So this is very analogous to the way that information is sent across a computer network. Within the packet, in the destination field, there'll be something that identifies the application, and we can say that's, in this case, Damien Roth in our analogy. The application that it's destined for might be web traffic, or it could be database traffic, but there'll be something that will identify it as a particular application. Then there'll be an additional piece of information that will identify the IP address, the unique number that's associated with the machine that application is running on. And there'll also be something that will identify the sort of the general area, the network that you want to get to, the specific network out of all of the possible networks that you could get to. So this is very analogous to the way packets get routed throughout a network. And one of the other questions I get asked when I start to discuss this is, well, why do we have these Ethernet addresses and IP addresses? There seem to be so many of these things. Why is it all so many of them and so complex? Well, part of it is historical, but there are very good reasons to have all of these addresses. So let's just delve into that a little bit more here. So what we have here are two computers connected to a piece of networking equipment. In this case, it's a layer 2 switch, and we'll talk about those much more later on. But just for now, it's a piece of networking equipment that enables these two computers to communicate if they know how to. On each of these computers, there's what's called a MAC address, or sometimes the Ethernet address. This is a globally unique number that's assigned by the manufacturer of that Ethernet card. Why do we have these addresses? Well, back in the mist of time when networks were just small number of nodes, Ethernet was a great technology. It's plug and play, meaning that you could just plug these devices into the network switch. They would send a broadcast, meaning sending out information to all nodes attached to that switch, and they would discover each other. And that's very much how the first network that I managed operated back in the 80s. The problem with that, though, is that sending broadcasts, each time you add a new PC to the network, you're adding more broadcasts, and you pretty much hit scalability problems straight away. And the first way we addressed that was to partition these switches into different little networks so that the broadcasts could be contained. And that's another function that the switch performs. It can separate things into a red network and a purple network from a broadcast domain perspective. So all of that was kind of okay. But then came along the big internet, and that pretty much changed everything. So we've now got these devices on these separate networks, and they want to connect out to the big internet to get onto all of that useful information and useful applications and tools that we now know and love. The way we would do that would be to connect these different networks into a router, and the router would provide the connectivity to the internet. Now, to do that, we need IP addresses. So we had to allocate to each device an IP address. Now, if you think about it, if we had tried to continue the model of Ethernet connectivity with lots of broadcasts, there's no way we would have been able to get a broadcast domain to spread into the internet. There would have been just too many hosts, billions of hosts, hundreds of millions of hosts, all trying to broadcast to each other and discover each other. That just doesn't scale. So what we have to do is add IP addresses, and that is a layer of hierarchy. Whenever there's a scaling problem in networking, hierarchy is always the solution. So with IP addresses, what we can do is identify these IP network numbers, and out on the internet, devices can send data packets towards these network numbers without having to know all of the details of the individual IP addresses or the MAC addresses assigned to each device, and that helps it scale. Okay, what are these packets? So let's delve into this a little bit more. So packets consist of ones and zeros, binary, the only language that computers understand. And those are typically sent out for Ethernet, at least, on wires with a 3-volt signal representing a 1 and a 0-volt level indicating a 0. Those collections of ones and zeros can travel on electrical wires, and they get seen at the other end of the communication, whatever is connected to the other end of that Ethernet wire. What that means we can do is that we can group these collections of ones and zeros into packets, which are defined ways of organizing data. So a packet will consist of a whole bunch of ones and zeros. Some of those ones and zeros will represent the destination address, some of them will represent the source address, the destination application, and so forth. So what that enables us to do is, if we have a JPEG file and image of some flowers. Very nice. We want to send it to someone, let them know we're thinking of them. What the computer will do is break up all the ones and zeros that represent that flowers JPEG file into different packets, and then send each packet from source to destination. The destination will receive them and reassemble them into an image. So that's how packets are formed and transferred across the network. If we look at how this is handled as the data traverses the network, we have a whole bunch of these things called headers. Now bear in mind, on the wire all we'll see is ones and zeros. If we could look into the computer itself, once it's received all of these ones and zeros, we would see that it has arranged these ones and zeros into frames first of all, and the frame will define the destination MAC and source MAC address. And within the payload there will be a packet. That's the layer 3 packet. If we expand that layer 3 packet out, we see we have a source IP address, a destination IP address, and so forth. And within the packet there will be a segment of application level data. That segment will identify the source port, the source application, and the destination port, which relates to the destination application. So here you can see we're just expanding out the payload, and each payload adds more specific information as the packet travels closer to its destination. So that's what I want to cover in this brief introduction. What we're going to do next is have a look at how these network numbers actually get represented in a router, the device that's directing traffic on the internet.